Good afternoon, everyone. I'm Michelle Sanner, and today we are going to be talking about the bond dipole. So by the end of this session, you'll be able to predict the direction of the bond's dipole in a covalent bond. So first, let's just review what the covalent bonding is. Remember, there are two types of covalent bonds, and these are bonds that form between a nonmetal and a nonmetal. You can have a nonpolar covalent bond in which your electrons are shared relatively equally and have similar electronegativity. So two elements that are equal to attract electrons to themselves in the same ability are considered to be nonpolar. When you have a bond between two elements that have a large discrepancy in their electronegativity, we call that a polar covalent bond. And what that means is that those electrons are being shared unequally between those two different elements. So to determine polar covalent or nonpolar covalent bonds, we need to look at the electronegativity values, the Pauling scale values for each of these atoms and compare and contrast the two. So let's talk today about what a dipole is. A dipole is a vector that we draw to basically indicate how charge is distributed within a bond. Polar covalent bonds, they tend to create uneven distributions of charge based on that unequal sharing of electrons. So you might have one atom that has a lot more electron density, that is to say, electrons are likely to be around it more often than they are with the other atom. And so this creates an imbalance in charge. So a dipole is created by equal yet opposite charges that are separated by a short distance within this bond. So here's an example of two molecules, molecule A, molecule B, sharing a bond. We can see that this is the more electronegative element. And the reason that I know that is because the element has a partial charge. Remember that this lowercase delta means partial. It's not a full negative charge because I haven't transferred electrons from the other bond to this, or from the other atom to this atom, but rather it's slightly negative because electrons tend to spend more time nearby atom A in this case. Atom B is the less electronegative element, and so it has a partial charge that's partially positive. And by convention, we draw this dipole arrow here. We always draw it in such a way that it's pointing towards the more electronegative element, and we cross the little tail at the end to indicate that that's where the partially positive side, or the less electronegative element. So it's a convention of identifying the more electron-dense region of an atom. So, like I said, the dipole is indicated with an arrow pointed towards the more electronegative and thus more negatively charged element in a bond. You make a small crossed tail on the end of the less electronegative and therefore more positively charged element within a bond. So these dipole forces drawn with arrows are an example of a phenomenon we call vectors. Vectors are arrow notation that symbolize both the direction and magnitude, magnitude being how much. So small dipoles will be indicated with small arrows. Large dipoles will be indicated with large arrows. So magnitude is shown by making an arrow longer or shorter. So things that have a very small electronegativity difference will be indicated by a short vector, a short dipole, and things with a big discrepancy in electronegativity, where the difference between the two is very large, will be indicated by a larger arrow that shows more magnitude. Also, the direction the arrow points gives you information as well. That's why we point it in this direction. So these are, of course, from your book, the text Holt of 2006. So dipoles can be added up. Dipoles of individual bonds can be added up, and just like other substances with magnitude and with direction, and we can find out where in a molecule that has many different atoms, there's a greater electron density. So molecular polarity, an uneven distribution of charge, that is an uneven distribution of electrons within a molecule. The result is a molecule that has one side that is slightly more positive in nature, one side that is slightly more negative in nature. So when you have a polar molecule, you end up with regions of more electron density and less electron density, making it have a partial negative charge or partial positive charge on either end. So we'll look at some examples here. If we wish to draw the dipole for this bonding pair of hydrogen and chlorine, well, I think we should start by checking the Pauling scale and determining what the electronegativity values are for this. So I'm going to look up hydrogen and chlorine. I see that hydrogen has an electronegativity value of 2.1. Chlorine there at 3.0. So 3.0 for chlorine, 2.1. By convention, we will draw the dipole pointing towards the more electronegative element, chlorine, and by convention, we will cross the tail at the less electronegative element, hydrogen. So we're pointing towards the arrow, pointing towards the direction where electrons are more likely to be in this bond. Let's do the same thing with carbon and oxygen. Again, I'm going to need to figure out what the electronegativity values are. Carbon is 2.5, oxygen is 3.5. So if I were drawing a dipole for this bond, I would point it again towards more electronegative oxygen and cross the tail at less electronegative carbon. Once we've identified each individual dipole, as we did here, we can add them up and see what dipoles exist overall in a molecule that has multiple bonds. So let's try that out. When you have molecules that consist of more than two elements, we need to take into account all of the dipole forces and kind of add them up in such a way that we determine the dipole of the overall molecule. Now, because dipoles are vectors that include magnitude, they have direction, they have magnitude, and they can be added together. The way that you add vectors together very easily is to basically start, here's a dipole, and here's another dipole. I'll draw the first dipole, and then I will draw the second dipole beginning at the end of the first. There it is. And then my total dipole will be simply the start, where I started from, and where I ended at. And it's that simple. So by adding these two blue bonds, these two blue dipoles together, I end up with this yellow dipole. In this case, this represents the molecular dipole. And those first two blue ones that I drew to get to that molecular dipole, those represent the individual bond dipoles. And this is a great two-dimensional example, but it gets a little bit more tricky when you're working in 3 dimensions and trying to add vectors that occur in 3 dimensions instead of these 2 on the paper. So your sum of individual bond dipoles will give you your molecule's overall molecular dipoles. You're just adding those vectors up. So let's take a look at some more examples. Here's ammonia, and this is tricky because we actually are working in 3 dimensions here. We've got a dipole pointing slightly up here, slightly up there, slightly up there. All 3 of those things coming in at equal angles are going to give you an overall dipole also pointing up. So when you're identifying the molecular dipole for multiple different bond dipoles, just try to point it generally in the direction that they're all going. But sometimes dipoles are going to cancel each other out. So if you have 2 dipoles, like here in carbon dioxide, that are equal in length, but pointing the opposite way, they're going to cancel each other out. For example, if I were to draw the first dipole going that way, and then I draw the second dipole on top of it, it goes back the same amount. My total distance traveled, the sum of these 2 dipoles together, is 0, because I'm basically ending exactly where I started. It's like taking 2 steps this way and 2 steps back the other way. And that's a good example of what happens when dipoles cross out. So this means that there is no net dipole for this symmetrical linear molecule. And we'll find this to be the case as we explore molecular geometries a little bit in future days, that there are some specific geometries where the dipoles cancel each other out. So we don't need to memorize this necessarily, but we do need to be able to do a few things to identify the individual bond dipoles between two elements, and then estimate the overall molecular dipole on a molecule as a whole. So that's a little bit about dipoles. We'll pick this up with a lab activity, and then we'll follow it up with some more activities and notes on geometry of a central atom, just like these examples here. And then we'll be able to predict the overall geometry and overall dipole of a molecule. So I hope you're doing well. Have a great day, and I'll see you soon.